In this video, we want to discuss the other types of surface forces. So far, we've been introduced to the normal force, and I said that it only applies to horizontal surfaces. That's actually an oversimplification, and I'm going to explain what I mean and why I described it that way. So in the previous video, we said that if you take a horizontal surface and you put an object on it, that's standing upright, it's not tilting or it's not leaning, then this object can be described as perpendicular with respect to this surface. If we draw a line here that's dividing it into half, we can see that it's symmetric. This little box is not leaning one way or the other. So there's 90 degrees between this midline and the horizontal surface. So I said that then there would be this normal force, and it applies to something that is 90 degrees with respect to the surface. So in this case, the normal force, I'm just going to put it off to the side here, would be pointing upwards. If this is the free body diagram, this would be the normal force. And it's balancing out and countering the weight force. So it's just like when you're sitting in your chair and gravity's holding you downwards while the chair is pushing back upwards. And so that's 90 degrees with respect to a horizontal surface. And I said that it had to be a horizontal surface. That's actually an oversimplification. I also mentioned that we would discuss in a future video what the situation would look like if you have some sort of banked surface here. So now let's look at this case and see how the normal force applies here. So the normal force still needs to be 90 degrees with respect to the surface. So if this was on an XY axis, this line would be pointing upwards at some angle, theta, with respect to the y-axis and with respect to the x-axis. And we could describe this line using our trig functions, our sines and our cosines. But what would happen if we instead tilted our head a little bit when we're looking at this line? Well, if you tilt your head to the left as you're looking at this line, at this banked line, you can see that it basically becomes horizontal. It's just having to do with your perspective while you're looking at it. And if that's the case, if all this line, this angle just really depends on your perspective, on how you're looking at it, well then it's not unreasonable to say that we could draw an XY axis that is in line with this banked line. So we could have an x-axis that's running parallel to the line, and we could have this y-axis which is running perpendicular. And this is just a new coordinate system, and you might be like, wait a minute, I can't do that. We can't just change our coordinate systems. But remember that we define x and y. We define what a positive angle and what a negative angle means. These are all things that we define. What you have to do is stay consistent once you define this. But we're looking at this banked angle now, and we can see now, according to this coordinate system, well, this line is horizontal from the x-axis perspective. And if you put a person on there, or an object, like let's say we just put another box and it's sitting right here. Assuming the box isn't sliding, well, now this box is normal to this surface from the perspective of this new coordinate system, as if you just tilted your head. So now we have the same situation that we have over here. So now these situations are the same if we're considering this as some rotated axis. Okay, so why would we bother talking about that? Why am I bringing all that up? Well, I'm bringing that up because now the normal force points still perpendicular to this surface, so it would point parallel to this midline on the box. But which direction does gravity always point? Gravity always points to the center of the Earth. what this would look like then is you would have something that is pointing straight down like this. So it's not parallel with this normal force. So here's the normal force. And now this is the weight force due to gravity. And they're not parallel. They're not the same line. They're not parallel. So this situation now is a little different. And the reason I didn't bring this up in the previous video when we were discussing these new types of forces is I didn't want to overcomplicate what was already a pretty complex video with some different ideas in there. So the normal force is a force that's perpendicular to a surface. So if you have this surface and then you have an object, well, then the normal force is going to point perpendicular to the surface. If you have a horizontal surface and you have an object, well, the normal force points perpendicular to the surface. So the line doesn't have to be horizontal. It can be a banked line. This line is going to be a little bit more complicated because we cannot say, in this case right here with this banked line, we cannot say that the weight force equals the normal force. They are not equal. The magnitudes, in other words, how big the weight force is does not balance out the normal force. Over here on this side, in this case, the force of gravity is parallel to the normal force. So the magnitude of the force of gravity is equal to the magnitude of the normal force. That is not the case over here where we have this banked surface that's at some angle. Okay, so that describes the normal force then. So the normal force still acts when we have this banked surface. It's going to still be pressing upwards. You could be sitting here on this box, and obviously the box would still be pressing upwards on you. You would still feel something that's pressing upwards on you that's preventing you from falling down through the earth. So that's the normal force. And now I'm going to describe the other two types of surface forces. So the normal force points perpendicular to a surface. Well, there is another force that points parallel to a surface. So if this is your box on a surface and you have some weight force that's holding the box down on the surface, and you have a normal force that's balancing this weight force. And if this box was really heavy and you came in here on the left side and you wanted to push the box to the right. So we want to push the box to the right and it's really heavy. Well, as you start pushing on it, you're going to have some force that is moving to the right because this person's pushing on the box. There's going to be some applied force to the right. And if the box is really heavy and it doesn't move, well, if it's not moving, then we have to balance out this force over here. I'm going to call this F push. So we have the force that's being applied here that's pushing to the right. And if it's not moving, we know that F net has to be 0. So we know that F net is equal to 0 since it's not moving. So I need obviously some vector to counter this F push. And the name of this is the static friction force. We describe statics and dynamics. We're just using that word again. Static in this case means not moving. And this force is usually given the little symbol of a squiggly F. And we can give it a sub S for static. And it's a vector. And all this means is this is the force that is countering this push when this box is not moving. So if this is what it looks like when the box isn't moving, well, what happens when the box actually starts to move? So here we had F net equals 0 when the box is not moving, and we had some static friction. And so now we want the box to move. So we have box moving. And we have a similar situation here. We have a surface, and the box is sitting on it. We still have the normal force that's pointing upwards, countering the force of gravity that is pointing downwards. And now let's think about this. We want the box to move. So we're starting from rest. And this person comes along and they want to push on this box to make it to move. So initially, we need this box to accelerate. It's starting from 0. This person is pushing on it. So it needs to accelerate. So to make the box accelerate, so for acceleration then, F net does not equal 0. So the person starts to push and they give it a big push to the right. And F net is not equal to 0, so this is F push. Then there's still going to be another force that's countering F push, but now F net is not equal to 0, so these are not the same length. If you would add this left vector and the right vector, the left one's negative, you would not get 0. The right vector is longer. So at this moment, when we're trying to accelerate the box and we push on it, F net does not equal 0. In this case, this vector now, we give it a new name. It's called squiggly F sub k for kinetic, the force of kinetic friction. And kinetic means moving. Now, immediately after the box starts moving, if F push remains larger than F sub k, then you'll continue to accelerate. You'll keep getting faster and faster and faster and faster. But you can reach a point where you're still moving to the right, but now the force of the push is equal once again to the force of friction. And you're not accelerating any longer, but you're just moving forward at a constant speed. So what would that look like? Well, it would look the same as the diagram on the left-hand side over here. So we would still have an F push, and it would be to the right. And now you'd have an equal vector pointing to the left, because now we're not accelerating anymore. This is still a force of kinetic friction, but now we have constant speed. So now we have constant speed, and we know from Newton's second law, if you have constant speed, well, then there's no acceleration and there's no net force. So since there's no net force, well, this makes sense because the force of kinetic friction is equal to the pushing force, but we're still moving at constant speed, so we still use kinetic friction because we have movement. We don't go back to the force of static friction where it's also F net equals 0. So this case is also F net equals 0, but this is constant speed. We're still moving. We're not accelerating. This is like maintaining 60 miles an hour on the highway. You're not accelerating, so there's no net force moving you and accelerating you forward. So these are the three different cases here. So we have the case of static friction where the box is not moving, the object's not moving, but we have some applied force. And to counter that applied force, the box, so it's not moving, has to have some other force pointing to the left that's countering that force. That's the force of static friction. Then we have a box that is accelerating, where the force of the push in one direction is larger than the force of kinetic friction. So we have acceleration. This is the case where F net does not equal 0 because we have acceleration. Then if your force becomes equal to the force of kinetic friction, well, that's the case of constant speed. This would be no longer under acceleration because F net equals 0. The force of the push is equal to the force of kinetic friction. So this is constant speed. We're not accelerating forward. In the next video, I'm going to discuss the different equations that describe the force of static friction and the force of kinetic friction. The equations are basically the same, but there's just some different concepts that we use to differentiate the two cases, where one, we have an object that's not moving, and the other one, we have an object that's in motion, either accelerating or moving at a constant speed.